Welcome to this lecture series. In this lecture, we'll talk about infinite sets. We will define them and prove some very natural and important properties. And then we will look at finite sets. So let's get started. We need to know about the language of sets and functions. Especially, we need to be familiar with these three notions: injection, surjection, and bijection. And I may add pre-image and image. Yeah. And domain, etc. Basic terminologies associated with functions. All of this is available in the playlist named Kickstart. There are some 3-4 lectures on sets and some 4-5 lectures on functions. All right. So, what is an infinite set? So, a set is called infinite. A set X is called infinite if it is in bijection with a proper subset of itself. Okay? So that's the definition of an infinite set. It's a beautiful definition. It is somehow saying that infinite sets are inexhaustible, and it is capturing that very nicely. Okay, so just pause for a moment and appreciate how beautiful and clever this definition is. Note that we are not defining a finite set before we define an infinite set. We are directly defining an infinite set. Okay. So just to spell this out a little bit more, we say that X is infinite if there is a proper subset A of X, or maybe better to say X prime of X, such that there is a bijection between X prime and X. That is what an infinite set is. So let's see an example. The set of natural numbers is infinite. Why is that? So the set of natural numbers is kind of your poster child for infinite sets, as we will see. So how do we show this? Just consider this map. Or maybe I'll do it the other way around. It's the same thing, but... So how do we define it? Just send n to n minus 1. So this is of course a proper subset of that. And the function f is clearly an injection. Why is it a surjection? Well, if you substitute 2, you get 1. You substitute 3, you get 2, and so on. Oops, what have I done? Yeah, you get 2. So therefore f is a surjection, and hence f is a bijection. So there is a bijection between the set of naturals and a proper subset of itself. And therefore, the set of natural numbers is infinite. Okay, now we have a very simple lemma. If we have an infinite set, suppose A is an infinite set and it is contained in some set, then the containing set is also infinite. This is intuitively obvious. All we are saying is that if something contains an infinite set, then that something should also be infinite. Anything that contains infinity should itself be infinite, right? So that is what it is saying, but of course one needs to supply a proof. And it's very simple. So since A is infinite, there is a proper subset A prime of A such that A prime is strictly contained in A and there is a bijection between A prime and A. So perhaps a picture would help. This is our set X, that is our set A, and somewhere we have A prime. This is X, this is A, and that is A prime. And there is a bijection between A prime and A. So there is some map which kind of expands this blob out and converts it into this blob. All right. So we need to find out a proper subset of X that is in bijection with X. And that is not a mystery. So define X prime as A prime union that thing. So X prime is this union the thing on the outside, which I'm shading. That is what is X prime. Okay. And now we will define a bijection between X prime and X. So define a function g from X prime to X as follows. So g of X is equal to, maybe I'll not write X, I will write maybe, what's a good symbol? Let me write X prime. So g of X prime is, this is equal to f of X prime if X prime is an A prime, and equal to X prime if X prime is in this part. So there are two parts, these are disjoint, A prime and that are disjoint of course. So if your input is from A prime, then just use the function f to send X prime to wherever. And if the input is coming from outside of A, then leave it as such. So this may look convoluted, but all that is happening is if you have a point here, we will leave it here. But if we have a point here, we will use the function f to put it inside this larger set A. Now it should be pictorially or intuitively clear that G is a bijection because outside of the blob A, there is obviously nothing to worry about. Everything is fixed. So outside the blob A, the function G is injective and surjective. Inside A prime, when your input is coming from A prime, it is basically emulating the function f, and f is a bijection. So the A prime bijectively maps to all of A. And therefore G is a bijection, and you can formally prove this by, following the steps. So just check that G is a bijection. And one more comment, X prime is a proper subset of X because A prime is a proper subset of A. Right? So that's it. So this shows that if some set X contains an infinite set, then the set X itself is infinite. Okay. So this allows us to say that the set Z of all the integers is also infinite because it contains the set of natural numbers. We just showed that natural numbers are infinite, and anything that contains an infinite set is also infinite, and therefore the set of integers is infinite. Similarly, the set of rationals is infinite because rationals also contain natural numbers. So that's that. And here is a little bit more general version of this lemma. You have an infinite set and we have an injective function from an infinite set to any given set X, then the given set is also infinite. So this is same as this lemma, except that, note, if you have an infinite set A, then an injective image of it is also infinite, clearly. Okay? Therefore, the set X contains an infinite set, namely the image of A, under the map F, and hence X is infinite. So this is essentially the same as that lemma. Okay. Now here is perhaps the most important theorem of this lecture. We have some non-empty set. Then the set X is infinite if and only if one can find an injection from the naturals into the set X. Many times in textbooks, this is how infinite sets are defined. We define an infinite set as a set in which you can embed a copy of the naturals, meaning you can find an injection from the naturals into it. But we took a different route. I find the definition of infinite sets, the one we gave, very, very pleasing and beautiful. So I started with that, and I proved this as a theorem. Okay. So this should be intuitively very, very appealing and obvious, maybe. But one needs a proof. In terms of the definitions that we made, intuition is not sufficient. We already have seen one direction. If we have an injection from an infinite set into a set X, then the set X is infinite. That we just remarked. So that part is clear. So we will prove the other direction. We will start with an infinite set and show that there is an injection from the set of naturals into the set X. So I want to show that there is an injection from naturals into X. All right, this is what we want to do. So since X is infinite, first of all, we will just change a little bit of notation. So set X naught is equal to X. And since X naught is infinite, there is some proper subset of X naught and a bijection like that. And let me draw a diagram. So this is our set X naught, and this is X1. Okay. Let us also fix a point. So let X naught be chosen like this. So the point X naught is here. Okay, it is outside X1 but inside X naught. We can do this because we have a proper containment. Okay, now define X2 as f inverse X1. So f is a function with domain X1 which maps the entirety of X1 bijectively onto X0. But since X1 is a subset of the target, X0 being the target of F1 I mean, X0 being the target of F1, and since X0 contains the subset X1, we can take its pre-image. Alright? And obviously, the pre-image of anything will be contained in the domain of F1. So this is clearly contained in X1. This may seem trippy, but there is nothing trippy going on. Okay, so far so good. Now the point is, define F2 from X2 to X1 as F2 is defined by just restricting F1 to X2. So F1 is a map with the entirety of X1 as its domain, but we restrict F1 to X2. So let me draw X2. Oops. Something like that. Now the figure suggests that X2 is a proper subset of X1, and we will prove it, but as of now, the figure has not been justified. So first of all, F2 is surjective. Why is this? So to see this, let we choose a point in X1 arbitrarily. Now since X1 is after all, okay, Y1 is after all a point in X0. Anything in X1 is in X0. So Y1 is a point in X0, and therefore, by surjectivity of the function F1, thus there is some y in the domain of F1 such that Fy is equal to Y1. So what are we saying? We chose a point y1 from the set x1 arbitrarily, but think of y1 as a point in x0 rather than x1. Now, since this map is surjective in particular, there is something in x1 that maps to it under the map f1. And that's something we have named as little y. But what does this mean? This implies that little y lies in f inverse of x1 because y1 lies in x1. Therefore, little y lies in x2 because f inverse x1 is by definition. Okay, I mean f1. Whenever I said f, I meant f1. Sorry. So yeah. So this means that y lies in x2. But finally, we rewrite our equation. Y lies in x2 and we have this equation. But once y lies in x2, f1y is same as f2y. Because f2 is just the restriction of f1 to x2. So we have shown that there is a point in x2 that maps to y1 under the function f2. And that proves the surjectivity of f2. Injectivity of f2 is clear because after all f2 is the restriction of an injective map, namely f1. So f2 is also injective. Being the restriction of an injective map. And we conclude that this is a bijection. So thus f2 is a bijection. Okay, that much we have. Finally, we want to show that x2 is a proper subset of x1. So this will be a final thing, for not really a final thing, but a most important step. So now we show that, how do I write this? We show that x2 is properly contained in x1. Okay. So let x1 in capital X1 be the unique point, be the point, let me just say that, be the element such that fx1 is equal to x0. f1x1 is equal to x0. So what are we saying? x0 is a point in the set capital X0, and since this guy is a bijection, there is some unique point inside the set x1, the domain of f1, which maps to x0. We claim that this is not in x2, right? And let me say why. If this were in x2, if the point x1 lied here, then what would happen if you apply the function little f to it? I mean f1 to it. Applying f1 to x1 is same as applying f2 to x1 because it lies inside x2. f2 is just the restriction of f1 to x2. So if you apply f1 to the point x1, you will land inside x1. You will not go outside x1. Right? And therefore x1 cannot be here. If it were here, then applying the function f1 to it would give us something inside x1. But applying the function f1 to it also gives us x0, which is outside x1. And that would be a contradiction. So that justifies this step. And that also justifies this diagram. Okay, and so we can write in our diagram that x1 is somewhere here. Outside x2, but inside x1. And at the same time, we can also indicate that, I wanted a curly thing. Yeah. x1 goes to x0 under the map f1. Now just consider the fact that f2 is now a bijection from x2 to x1 and x2 is a proper subset of x1. So we kind of in the same situation, we are kind of in the same situation as earlier. Earlier we had this big blob and this small blob was mapping bijectively to it. We have replaced our big blob by a smaller blob and found one smaller blob inside it with the same property. So we can keep on iterating. So this way we can keep on going, creating x3 and so on, dot dot dot, difficult to make any more blobs. You can keep on creating them and finding these x2s and x3s and so on this way. And now we can find an injection from the naturals inside our set x0 just by mapping 1 to this guy, 2 to that guy, 3 to that guy, and so on. So that gives us an injection of naturals inside the set x0. x0 is same as x, and that finishes the proof. So that last line I'm not writing. I hope this proof was clear, and this is one most important thing from this lecture. Okay, let's move on. We can say a little bit more in the same context. We have a non-empty set. We fix something in the set X. Then the set X is infinite if and only if there is an injection from the naturals to X which maps 1 to A. So here we have just one extra condition that we can demand. And this is nothing. This is a very simple exercise given the previous proposition, but we will do it in full. Again, one direction is trivial. If you had such an injection with this property, then in particular you have such an injection. And by what we saw, if you have an injective function from an infinite set or from, in particular, the set of natural numbers inside any set X, the set X is infinite. So that direction is trivial. We will start with the assumption that X is infinite and create such an injection with this property. So assume X is infinite. We will create an injection phi with the property that phi of 1 is equal to A. So there are two cases. Case 1. Yeah, so before we start with case 1, so by the previous proposition, we can find an injection. Let f n2x be an injection. This exists because x is infinite and because of the previous proposition. We have that, and now there are two cases. Case 1. Case 1 is that A is not in the image of f. Okay, so let us try to draw a diagram. This is our set X, and A is somewhere here, and the function, this is the image of 1, this is the image of 2, this is the image of 3, and so on, dot dot dot. So in the figure, basically we are saying that f of I is equal to xi. Okay, and A is not in the image, so all of these dots are different from A. Okay, so we will just create a new function. To define phi from naturals to x as follows. Yeah, I think a very simple modification will do. So phi of n is defined as A if n equals 1 and f of n if n greater than 1. Okay, so that's how we define phi. Clearly phi is injective. Why is it injective? Well, it is first of all injective on this range. Whenever you feed two natural numbers which are both greater than 1, clearly they have distinct image simply because f is injective. And the image of 1 cannot clash with any of these because this was not in the image of f. So just justify for yourself that phi is injective. And by definition, phi of 1 is equal to A. So this finishes the proof in this case. If A is not in the image of f, we are clearly done. So case 2 is that A is in the image of F. Sorry, A is in the image of F. So here also there are two cases. If F of 1 is A, then we are already done, then clearly done. So assume F of 1 is not A, but since A is in the image of F, it will be the image of some point which is different from 1. So here we will just make a small modification to the function f, define the function phi from naturals to x as phi of n is equal to f of n if n is not equal to 1 and n is not equal to n naught. So in these two inputs, we just mimic f, a if n is equal to 1 and f of 1 if n is equal to n naught. Again, this may look complicated, but all we are saying is, what does phi do? It behaves exactly like the function f, except on 1 and n naught, the behavior is switched. Whatever f was sending 1 to, phi sends 1 to the image of n naught under f, and whatever f was sending n naught to, phi is sending 1 to that. So it's just flipping the role. That's all this is doing. And clearly then, it should be intuitively as well as technically clear that phi is an injection, and clearly it sends 1 to A. So that's it. This is a very, very simple proof, but since we have done it in full detail, it may look complicated. Okay, fine. So let's proceed. Now this is also very interesting. This says that if we have a non-empty set and some point little a in the set X, then the set X is infinite if and only if there is a bijection between the set X and the punctured set X. So you puncture the set X at A. This is the punctured thing. And X is infinite if and only if there is a bijection between X and that. So again, one direction is clear. If there is a bijection between X and that, then there is a bijection between X and a proper subset, and therefore X is infinite by definition of an infinite set. So we will do the other direction. So we will assume that X is infinite and show that there is a bijection between this and that. Okay, so we will use the previous proposition. By the previous proposition, we can find an injection such that phi of 1 is equal to A. Immediately from the previous one. And let's say y is equal to image of phi. Okay, now consider this diagram. We have this injection and we have this function, call it f, and what does it do? It sends n to n minus 1. That's this function. And what is, so this is just restriction of phi. Phi restricted to, so this symbol just means that we are restricting phi to that set. The domain of phi was entire n, but now we are restricting it to that. And here what we will get, this will be, if we write y minus a here, this becomes a bijection, right? Because phi was mapping 1 to a, and the image of n was written as y. So phi was bijectively taking n to y and 1 to a. So if we puncture n at 1 and puncture y at a, we will again get a bijection. So this is a bijection, and that we are denoting by the symbol, the fact that this is a bijection. Okay. And maybe I will write y here so that everything is a bijection. This is also a bijection now. So this is, let me just write it as phi even though we are changing the target. This kind of thing shouldn't confuse you. So this is a bijection, this is a bijection, and this is a bijection. Everything is a bijection here. So just define alpha. This is our map alpha. This is alpha. So alpha is defined as, you first go via the inverse of the restriction of phi, then you, So first you apply the inverse of the restriction of phi, then you apply f, and then you apply phi again. So what is this? First you go this way. Since this was a bijection, you can go in the other direction also. Just reverse this arrow. You go this way, then you apply f, and then you go that way. That is the map alpha. Now since this is a bijection, that is a bijection, that is a bijection, this is also a bijection. So alpha is a bijection. Okay, alpha is a bijection. And now finally define a map gamma, let's say, from the punctured thing to x. You can easily guess. Gamma of x is, maybe I'll take another line. Gamma of x is alpha x if x is in y minus a, and it doesn't do anything if x is outside y minus a. Right? So gamma is a bijection. Again, you can draw a picture. So this is x, and inside you have y, and here somewhere you have the point a. So what we have done is, what is gamma doing? It is taking y minus a to y bijectively, and everything outside is remaining fixed. So that should make it clear that gamma is a bijection, and we have created a bijection between x minus a and x. So all this reasoning again may seem complicated, but what are we doing? We first identified the image of naturals with the naturals, and all of this was just passing to the natural numbers. In the natural numbers, there is an easy way to map punctured n, punctured at a given point, to the set of natural numbers. You can very easily write down that function. Once you identify y with the natural numbers via the function phi, you can mimic the same thing in y after passing to the naturals, then getting this bijection, and then again passing to your original thing. Coming back to your original thing. So that's what is happening here. It may look like some complicated machine, but nothing is going on. Okay, mull over it. These things will become more and more clear. So this is a very, very beautiful statement. X is infinite if and only if you can bijectively map it onto any punctured version of itself. Not just any proper subset, but you puncture it at one point and it will be bijective to it. That's really, really amazing. Okay, now we can talk about finite sets. So what is a finite set? By definition, a set X is called finite if it is not infinite. So something very strange has happened. The notion of a finite set is intuitively much simpler than the notion of an infinite set. There is so much confusion around infinity in popular media that I have to break my head sometimes. But the route we have taken is that we have defined an infinite set first and then defined a finite set as negation of infinite sets. Usually one would think to do these things the other way around. Somehow define a finite set and then say if infinite sets are those which are not finite. But I like this route. Fine, so we have defined finite sets, and now here is a characterization of it, much in the same vein as we characterized infinite sets via natural numbers. We are saying a set X is finite if and only if there is a surjection from a finite, I shouldn't say finite, a chunk of natural numbers, 1 up to n. So let me read it out rather than fumbling. So a set X is finite if and only if there is some natural number n such that you can surject the first n natural numbers onto X. That's the definition, that's the theorem. The proof is very simple. Perhaps I'll just catch it. So if there is such a surjection, then x cannot be infinite. That should be clear. And for the other direction, suppose x is finite, then we want to prove that there is such a surjection. Assume there is no such surjection, and we have this blob to denote the set x. If there is no such surjection, then there is no such surjection for n equals 1. Okay, so fix a point x1 here, and this cannot be the entirety of the set x, because if it were, then there would be a surjection from this to x. So there are more things inside the set x. Okay, now there is also no surjection from this set to x, since we have assumed that this does not happen. There is no surjection from this to x, so we should be able to find a point x2 different from x1. And now since there is no surjection from this to x, we should be able to find a point x3 and keep going. At the end of the day, we will be creating an injection from the set of natural numbers to the set x, and hence x would be infinite, contradicting the assumption that x is finite. So that is the argument. If this was too fast, you can just take this part as an exercise. This is a very simple portion of this lecture. Alright, so with that I want to end this. As usual, like, comment, share, subscribe, and I will see you next time.